Hey there, students. On this clip, we're going to be going over an example on using the epsilon delta proof or the formal definition of limits to prove that the limit statement is true. All right, so let's go ahead and write down what the question is. So example, prove that, prove that the limit as x approaches 3 of the function x squared equals 9 using the formal definition of limits. Okay, so the informal approach, you just plug in 3 here and then you see that x squared equals 9, right? But that's not the rigorous. So I'm going to be showing you the rigorous proof that the limit as x approaches 3 of x squared equals 9. Alright, so before we start our proof, what we're going to do first is we're going to write down what the definition of limits is. Alright, so what is the definition of a limit? So let's write down the definition first. Definition. So let's say for a and L in R. You know what R means, right? Real numbers, okay? A set of real numbers. So we're basically saying that A and L are subsets of the real number set. Okay, so for A and L in R, the limit as x approaches this A value of the function f of x is equal to this L value, where my LL means, this means that for any epsilon greater than 0, write my epsilon well, for any epsilon greater than 0, you can think of epsilon as your neighborhood around your L value, which is basically 9 here. So we're basically creating an epsilon neighborhood around the L value. So for any epsilon neighborhood around this value that the function approaches, there exists another value called delta greater than 0. This is now your neighborhood around your x value that you're approaching, which is 3. So for any epsilon greater than 0, there exists a delta greater than 0 neighborhood around the 3, such that if you have a condition where you have a non-zero neighborhood, x minus a, known as delta, this implies that you have an f of x minus L neighborhood known as delta, epsilon. Okay, so the limit as x approaches a of the function equals L basically means that for any epsilon greater than 0, you have a delta greater than 0 such that this remark right here, having a delta neighborhood around A, implies that you have an epsilon neighborhood around L. Alright, so this is basically what it means. So for our proof, what we're going to try to show is that we have a specific delta that we can show that this implies that will conclude our proof. Okay, so with the use of this definition, we're going to assign certain values to certain variables so that we can apply this definition to this particular problem that we're dealing with. Alright, so with this definition in mind, what we're going to do, we're going to set A to 2. Why did we do that? Oh, I'm sorry. What am I doing? Set A to 3. Set A to 3. Why did I set A to 3? Because look at the definition. X is approaching A, right? And in our question, X is approaching 3. So the value that X is approaching is what A is, right? And then the function, we're going to set to x squared, because that's what the function is. And then we're going to set L to 9 because that's the value that the function approaches as x approaches 3. All right. So now using this assignment right here, what on earth are we trying to prove? So the goal, um, we need to show that for any epsilon greater than 0, there exists a delta greater than 0, such that, I'm writing in shorthand here, pardon me, such that this for absolute value of x minus a, what is a? A is 3, right? X minus 3 less than delta, this is the delta neighborhood around 3, so that if you have a delta neighborhood around 3, that implies that you're going to have an epsilon neighborhood around f of x minus L. What is f of x? F of x is x squared, right? So x squared minus L, 9, has to be less than epsilon. So basically you have an epsilon neighborhood around 9 if you have a delta neighborhood around, this implies that if you have a delta neighborhood around 3, that follows that you have an epsilon neighborhood around 9. Alright, so this is what we need to show. Alright, so in order to do this, what we're going to do is, we're going to write down part 1. Alright, so part 1. Okay, so let's write down what part 1 of this proof is. Part 1. So for part 1, what are we going to do here? What we're going to do in part 1 is we want to find the appropriate, pardon my weird writing, want to find the appropriate delta. Okay, so what we're looking for is the appropriate delta that can enable us to have this implied statement. Okay, the appropriate delta such that if x minus 3 is less than it, that implies that x squared minus 9 is less than epsilon. Okay, for some epsilon greater than 0. Alright, so how on earth do we find the appropriate delta? Now, one thing I want you to note is what we're doing right now is just scratch work. This is not the actual proof. As soon as we find the appropriate delta, then we can go ahead and construct the proof. Alright, so to find the appropriate delta, we're going to work backwards. Okay, so we're going to work backwards. We work backwards from f of x minus L is less than epsilon. Okay, so we're going to work backwards from this and then hope to find the appropriate delta to find the appropriate delta that will make us execute the proof. Alright, so let's go ahead and start from f of x, the absolute value of f of x minus L. This is working backwards. I hope you understand why I say work backwards, right? Because if you look at this implied statement, this is the hypothesis and this is the conclusion, right? But we're going from the conclusion to generate a hypothesis so we can use our proof to go the other direction. So this is the end right here, and this is the start. So since we're starting from the end, that's why we're working backwards, alright? So starting from the right side of our implied statement, we have this, f of x minus L equals E. Using these substitution values right here, I'm going to put them in. That's going to give me the absolute value of x squared minus 9 is less than epsilon. Alright, what can we do here? Oh wait, we can factor this. This is a difference of squares, right? So this becomes x minus 3 times x plus 3. Hopefully you remember how to factor difference of squares less than epsilon. So let me just put a side note here. What I just did is I just factored, okay? I just factored. Alright, so now, whenever you multiply two numbers, and you take the absolute value of the product, it's the same thing as multiplying the absolute value of the respective numbers that you took the product of. So the absolute value of x minus 3 times x plus 3 is the same thing as x minus 3 times the absolute value of x plus 3. And this is also less than epsilon. Alright? Now let's take a look at this situation right here. If you look at what we wanted, we wanted to bound x minus 3, right, to be less than delta, which shows up here nicely. But, oh wait, we have a problem. This is a problem right here. We need a boundary for this guy also. If this were just a constant like the linear proofs, all you just do is divide by that number and you're done. You know what your epsilon is, whatever you have here, you just set it as your epsilon. I mean your delta, you set that as your delta. But since we have another variable, another function here, we need to find out how to bound these two together so that we can have a proof. All right, so what we're going to do here is we're going to be creative. All right, so since we're getting really close, what are we getting close to? We're getting close to, in the problem, we're getting close to 3, right? So what we're going to do is we're going to pick a delta that's close to 3. All right, pick a delta that's close to 3. What delta can we pick? Well, how about pick a neighborhood that's 1 unit away from 3? Okay, so we can pick 1 unit away from 3. So in that case, we're gonna require that delta is less than or equal to 1. All right. You see this interval I chose? I could have selected 3, 4, 5, 6, 7. It doesn't really matter. They all work. But 1 is nice. I just like to go 1 unit to the left and right. Just the integer that's closest to that value. So I'm going to let delta be 1. Okay, so you're going to pick 1 unit away around the limit value that we're approaching. Okay, so if we select this to be my neighborhood, then that follows that you know that this value right here is strictly less than delta, right? So the delta is less than or equal to 1, then we know that x minus 3 has to be less than 1. All right? So if x minus 3 is less than 1, we have one boundary on our x based on this selection that we made. Okay, we actually constructed this selection. It could be any other number, but 1 is customary for problems like this. So we selected 1, and then that forces this to be less than 1 based on our construction. Okay, great. We have one piece. We have this constraint. Now how about this monster here, this problem? In order to do that, all we just have to do is solve this into x and see how we can express this using whatever x value we derive from here. So let's go ahead and isolate x here. So if you think back to algebra 2, how do you solve absolute value equations? Just make this a bounded inequality. So you have -1 is less than x minus 3, and that's less than 1. How on earth do you solve this? You just simply add 3 to all sides, right? So you add 3, add 3, add 3, and that gives you 2 is less than x, and x is less than 4. Okay, so if you have a 1 unit boundary around this, this is basically what it's going to look like. Because if you think about it, you just on 3, right? If you go 1 unit to the left of 3 and 1 unit to the right of 3, where are you going to be? You're going to be, so if you're at 3, you go 1 unit to the right, you're going to be at 4, right? Yeah, right? And then 1 unit to the left, you're going to be at 2. So that's basically what this inequality is saying. All right? So having found how constraint on x, can we construct this piece right here in the center? Absolutely. How do we do that? You just simply add 3, right? Add 3 to all 3 sides. So add 3 here, add 3, add 3 to the left side, to the rightmost side. Let me shift my 3 a little bit to the right so you don't get confused. So what have we created right now? Well, we're going to have 5 is less than x plus 3, and that is less than 7. We are concerned about creating an upper bound for x plus 3 because you know this is bounded below by 0. So this piece right here doesn't really count. So based on the fact that x plus 3 is less than 7, we can conclude that the absolute value of x plus 3 has to be less than 7 also. Okay? Because this piece right here is not what we're looking for. We're trying to bound this quantity from above. Alright? So now what we're going to do is as follows. If the absolute value of x plus 3 times oh wait, I just went ahead of myself. So what are we gonna do? Let's just rewrite what we had earlier. Let me take the if out of there. So basically we have we're going to go back here, x minus 3 times x plus 3. Let's bring it back down. I'm just going to go back to where I started from. X minus 3 times x plus 3 is less than epsilon. So I'm going to focus on just this right part here. So let me rewrite it. Remember, we're trying to bound it from above. So I'm going to put absolute value of x minus 3 here. So what do we know about this? Since this is less than that, what can we say about this right here? We know that this has to be less than the absolute value of x minus 3 times 7. How do I know that? Well, x plus 3 is less than 7, right? So if I just multiply both sides by the absolute value of x minus 3, this inequality holds because this piece is less than that and that is equal to that. So the product is going to be less than this, okay, using this info right here. All right, so I hope you see how this plays into this rule. It helps us find a value that limits this. So 7 basically is a boundary for the x plus 3. All right, so so if x minus 3 times 7 is less than epsilon, then what can we conclude? Because you know the goal is to make this less than epsilon, right? What can we conclude? Well, we can conclude that 7. Well, we can divide both sides by 7. Divide this by 7. Divide by 7. We have x minus 3. Then x minus 3 is less than epsilon over 7. Voila, that's exactly what we want. Remember, we're dealing with x minus a. If you look up here, we have, let me just call this the first constraint. Call it constraint 1. We had one constraint, but this wasn't sufficient because x plus 3 presented a problem, right? We had 2 quantities. Now, guess what? We have another constraint here, constraint 2, that can actually help us to solve the whole multiple constraint problem, all right? So what we're going to do is we're going to use these two simultaneously to find the appropriate delta, all right? And that will enable us to do the proof. So how can we use this and this to find the appropriate delta? We know x minus 3 is less than 1, and x minus 3 is less than epsilon over 7. So how can we make sure that these two, whatever value it is less than whatever delta we pick? So what we're going to force is we're going to, for the proof, and we're actually going to do the main proof. And I'm going to, when I start the proof, I'm going to show you what the appropriate delta is. All right, so this is the actual proof. Everything above here is all scratch work. All right, doesn't really count. It just helps me find the appropriate delta. Well, it does count, but it shows where my appropriate delta comes from. All right, so the proof is we are going to let delta be the minimum of the two boundaries on our x minus 3, the minimum of 1 and epsilon over 7. Okay, so that guarantees that I can be able to write my proof. So with this appropriate delta, then we can go ahead and write the proof. So with this constraint, with this value of delta, then we're going to have the absolute value of x. We're going to go x squared. Let's start with the original problem. X squared minus 9 is going to be equal to, we factor it again, x plus 3 times x minus 3, right? And that is equal to x plus 3 times x minus 3. And we're going to, well, we know that x plus 3 is less than epsilon over 7, right? So this is going to be less than epsilon. Wait a minute, x plus 3, well, this is less than 7 times epsilon over 3, so I gotta change, let me change this. This is less than 7 times x minus 3. Well, how do I know that this is less than 7 times x minus 3? Because above here we said x plus 3 is less than 7. So this component right here, we can put a 7. And we know that this piece right here is less than that. This is less than this because x plus 3 is less than 7. Alright, so that using this fact right here, I can make this conclusion right here. Okay, now I'm going to use the constraint on the x minus 3, which I kind of did earlier. I did it too fast. So the constraint on x minus 3 is epsilon over 7. So we know for sure that this piece is going to be less than 7 times epsilon over 7. Okay, because that's the other constraint that we have right here. We know x minus 2 is less than epsilon over 7, so this has to hold. And then you notice that you have a cancellation action happening here. 7 and 7 cancel out. And then we have x, this is less than epsilon, so we have absolute value of x squared minus 9 is less than epsilon, and that concludes our proof. Alright, so you notice how short the proof is, not too complicated as long as you have your appropriate delta. The hard part is working backwards and generating your delta values. Okay, so thanks for paying attention to this presentation. You can feel free to subscribe here by just clicking subscribe up here. You can share it with your friends via Facebook or our Twitter. Like my video, please, if you liked it. If you have any issues with it, just send me an email or post a comment and I'll be glad to address it. More videos are available on my.serve.com, so visit my site and have fun practicing mathematics. Alright? Thanks again for watching this video and have a wonderful day.